So hello, we'll be discussing about the chemical shift and also the factors affecting chemical shift in two parts. And this is the part one. So here, what do you mean by chemical shift? So what is the role of chemical shift in this NMR spectrum? So the chemical shift is generally denoted by the symbol delta and whose unit is actually ppm. What is that ppm? Parts per million. So chemical shift measurements are based on the resonance positions of the hydrogen nuclei with reference to a standard substance, TMS, that is tetramethylsilane. So the silicon atom surrounded by 4-methyl group. That is, the silicon atom is surrounded by generally 12 protons. Hence, the tetramethyl silane is highly shielded organic compound due to the presence of 4 CH3 groups. And any molecule will be resonating at a higher frequency at a higher frequency than that of the tetramethyl silane, as the diamagnetic shielding is very high for TMS. Otherwise, we can say that no other organic compounds have greater shielding than that of the TMS. So nothing can resonate before this compound. So every compound would resonate only after this tetramethyl silane. So for tetramethyl silane, a very sharp, intense peak will be observed. Generally, when NMR spectrum is recorded, say for example, 5% of this tetramethylsilane will be mixed up or it will be added with a sample, and this NMR spectrum will be recorded. So for tetramethylsilane, we'll be getting a very intense, sharp peak, and with respect to that position of that peak, the positions of the other hydrogen nuclei of the organic compound which is under analysis will be measured. So for tetramethylsilane, the delta value is considered to be 0 ppm. So chemical shift measurements can be said to be, it is the resonance position of the hydrogen nuclei with reference to a standard substance, that is TMS. It is the difference in the positions of the hydrogen nuclei with respect to TMS. So in practice, all the nuclei are associated with the electrons in atoms and molecules. So when they are placed in a magnetic field, the surrounding electron cloud tend to circulate, and they will be circulating in a direction so as to oppose the applied magnetic field, and that is said to be the diamagnetic circulation. In addition to that also, we get the paramagnetic circulation. So you could see that the electron movement that is circulating in this direction around this proton, it will be creating a secondary magnetic field. And this secondary magnetic field, which is produced due to the circulations of the electrons, when they are opposing the external magnetic field in this direction, you could see that they are moving in this direction, and this is the direction of the applied magnetic field. So hence this secondary magnetic field is opposing the applied magnetic field, hence they are said to be diamagnetic in nature here. But the same secondary magnetic field, when they are reinforcing with the of the applied magnetic field, otherwise when they are remaining parallel to that of the applied magnetic field in the direction of the applied magnetic field, then they are said to be paramagnetic in nature. So here the diamagnetic effect will be causing shielding, and here the paramagnetic effect causes de-shielding. So here the protons will be experiencing more magnetic field, they are said to be de-shielded, and here in this the protons are experiencing lesser magnetic field, hence they are said to be shielded. Thus the field felt with the proton is diminished, then the proton is said to be de-shielded. But if the induced field reinforces the applied field, then such protons are said to be de-shielded. Why? Because they could feel higher field strength. So shielding shifts the absorption upfield and de-shielding shifts the absorption downfield, which is actually, in order to cause the absorption, they need to get an effective field strength. So shielding will be absorbing higher field and de-shielding photons will be absorbing at a downfield. So such shifts, which is actually obtained compared with the standard reference in the position of the NMR absorptions, and which are arising due to the shielding of effect or de-shielding of the protons by the electron coupled to the chemical shifts. So here the total field experienced by the nucleus is given mathematically by V effective. The effective field strength experienced by any nuclei will be equivalent to the applied field strength, that is V naught minus B induced. So what is this B induced? It is the induced magnetic field because of the circulations of the electrons. And that B induced generally depends upon the screening constant, otherwise the shielding parameter, and also the applied field. So when we substitute this in the above relation, B effective will be equivalent to B naught minus sigma B naught. Hence B effective will become B naught into 1 minus sigma. Thus the nucleus can be said to be shielded from the applied field by a diamagnetic circulation. The extent of the shielding will be constant for any given atom in isolation, but they may vary with the electron density about an atom in a molecule. Why? Because this atom will be surrounded by the adjacent or neighboring atoms. So the electron density around this atom may be varying. So in a generalized expression, we could see that Bi is equal to V naught into 1 minus sigma I. So Bi is the field expressed by the particular nucleus I, and sigma I is the shielding constant for the nucleus I, and V naught, we know that it is the applied magnetic field strength. So we can take an example of methanol and let us see how the applied field strength actually varies the positions of the nuclei in the NMR spectrum. So the effect of the applied field strength on the hydrogen nuclei of methanol. So we could see that two types of protons are present. One which is attached with oxygen, the other one which is attached with the carbon. So this proton will have a different electron density when compared to this methyl proton. So we need to see that the attached atoms to the protons. So carbon and oxygen. Compared to carbon and oxygen will be highly electronegative. Since it is highly electronegative, it will be pulling the bonded electrons towards itself. So the electrons surrounding this proton will be very less. If the electron density is less, then they are said to be de-shielded. There are no electrons in order to hinder the protons from being experienced by the applied field. And here, the carbon atom, which is lesser electronegative than that of the oxygen, it could not pull more electrons towards itself. So these protons are surrounded by higher electron density than that of hydroxyl proton. So this proton are said to be shielded. Why? Because they are surrounded by the electrons. So those electrons will shield the proton from being experienced by the applied magnetic field. So the shielding constant for this methyl proton will be very, very higher compared to that of the hydroxyl proton. So we could see that the shielding constant for this CH proton is very high than that of the hydroxyl proton. So when you are substituting this in the relation, then mathematically we'll be getting higher value for the applied, the higher value for the OH protons. So the field for the OH protons will be higher than that of the field experienced by the CH proton. So the effective field experienced by the hydrogen nucleus in OH bonds is greater than at the same nucleus in the CH bonds. So let us illustrate in the coming slide. So we could see that hence for a given applied field, the CH hydrogen nucleus will be processing with a smaller, lower frequency than that of the hydroxyl proton at a particular frequency of 100 MHz. A CH hydrogen, therefore, it will be requiring a greater applied field than the OH. So here we could see that the CH hydrogen nucleus, which is actually said to be shielded, it will be circulating with a lesser lower frequency. Why? Because it is not experiencing much of the applied magnetic field. So it will be processing with a smaller lower frequency. So here OH hydrogen nucleus has a smaller shielding constant, but that will be experiencing a greater field. Hence, its energy levels are more widely spaced than those of the more shielded methyl nuclei at a given applied field. So OH hydrogen nucleus, since they are actually having a lesser shielding constant, means they are actually de-shielded. Why? Because the electrons are attracted towards the oxygen. Hydrogen is free from the electron density, hence it is said to be de-shielded. So it could experience the applied magnetic field to a greater value. So when they are experiencing a greater field, the splitting will be maximum. So you could see here the splitting of the two states, alpha state and the beta state, the splitting will be maximum for the OH proton as they are experiencing a maximum or a greater applied magnetic field. But CH3 proton, they will be experiencing a lesser magnetic field strength, hence the splitting will be somewhat lesser than that of the OH. So the energy difference between CH3 energy levels between CH3 due to the CH3 protons will be very less than that of the hydroxyl protons. So in such condition, if the system is irradiated with a beam of radiation, say for example 100 megahertz, while the applied field is increasing from 0, you could see that here no field, there is no any splitting, but in the presence of the field, the splitting actually happens. So the field strength could be increased from 0 to increasing in this direction. So the OH nucleus will come into resonance first. So you could see that here the OH protons energy level difference actually matches with it of the frequency of the applied frequency of the applied radiations. So it will be resonating in the lower applied magnetic field itself. In the beginning itself, it will be absorbing the radiation, means it comes into resonance in the beginning itself, means in the low field or down field itself, it will be resonating as it actually experiences a greater magnetic field. So it is enough for it to get a minimum applied field to cause a resonance or to cause an absorption compared with of the CH3 protons. So CH3 protons will be absorbing a very high magnetic field as they are experiencing lesser applied magnetic field as they are shielded. So here methyl proton will be absorbing in as an upfield. So shielding nucleus will resonate to a high field, and otherwise they are absorbing in the upfield. So the chemical shift difference, so delta. So you could see here the difference between the hydroxyl proton and the methyl proton. It is represented by delta. That is the difference in the positions of these two signals. So the chemical shift difference delta between the OH and CH3 is observed in Tesla scale. Why? Because the spectrum is already recorded by varying the magnetic field. Therefore, here for methanol, delta is found to be 3.26 microtesla. But the spectrum can also be obtained by varying the applied frequency at a constant field. As we know, NMR spectrum can be studied under two conditions. One, by having a constant frequency and varying applied field, otherwise by having a constant applied field and varying the frequency of the radiation. In two ways we can study the NMR spectrum. So in the earlier case, we had a constant frequency of 100 megahertz and we varied the applied field strength, and based on that delta you got it as 3.26 microtesla. But the same experiment can be done by varying the applied frequency at a constant field. Then the chemical shift difference delta can be obtained in terms of hertz. So we know that 2.387 Tesla is equal to 100 megahertz. So this calculation is actually obtained from this relation, known relation in the earlier slides we had seen. So mu is equal to delta E divided by H. That is nothing but G, the gyromagnetic ratio of the proton, G factor for the hydrogen, and Bohr magneton for the nucleus, into the applied field strength divided by H, the Planck's constant, then mu will be obtained in terms of hertz. So we could correlate 3.26 microtesla with hertz, that is 149 hertz. So chemical shift difference is found either way, as in terms of microtesla, otherwise in terms of hertz. But both the things, if chemical shift are measured either in terms of hertz or tesla, it is entirely not satisfactory. So we need to include the screening constant, that is the we have to take into account for any nuclei, we need to take into account the shielding constant also. So we know already delta E divided by H, the relation for the frequency in terms of G factor and also in terms of Bohr magneton, and the applied field strength H, and that applied the effective field strength due to the nuclei when we are substituting from the previous expression, Bi is equal to B naught into 1 minus sigma I. Then this sigma I, there are actually two protons, so sigma CH minus sigma O. So from this relation you could see that the chemical shift separation, since they are expressed in terms of hertz, and whatever here it has come in hertz, both can be equated. So the chemical shift separation delta in hertz also could be equivalent to these values. So it could be equated as this expression in terms of hertz. So from this we could see that this delta is directly proportional to this B naught, and sigma I, which is actually independent of the applied field or frequency. That is, the screening constant is actually independent of the applied field or frequency. They just depend upon the electron density, the shielding constant. But the chemical shift separation delta is measured in terms of hertz or microtesla, is directly proportional to the applied field V naught. Hence, it is convenient to measure a quantity which changes with the operating condition of the instrument, either in terms of the applied field or in terms of the applied frequency. In this case, we are just changing the applied field. So most of the instruments, they operate in a condition of varying the fields from 0.6 to 15 Tesla. So the chemical shift separation we'll be getting in terms of these variations in the applied field in terms of Tesla, which will be quite difficult in order to measure as the conditions will be varying from an instrument to another instrument. So we could not conclude in common the chemical shift difference values. So in order to get a generalized representation of this chemical shift difference, that is the difficulty can be overcome by quoting the chemical shifts as a fraction of the applied field or frequency. If we are calculating in that way, in either way, if you are calculating, the results will become same. So we can see in the coming slide. So the values of the chemical shift delta for any substance with respect to tetramethylsilane can be calculated as delta is equal to the frequency of the sample minus the frequency of the tetramethylsilane, the difference between the positions of these two signals in terms of frequency. So here you could see that this is tetramethylsilane whose chemical shift value is 0 ppm. So the frequency is actually increasing in this direction as well the chemical shift. So when we take the difference, that will be giving us delta mu, or is delta mu the frequency shift. And when we discussed the chemical shift to be, it is to be taken as a fraction of the applied field strength, otherwise a fraction of the operating frequency, then we can get in terms of the chemical shift value in terms of ppm. So the operating frequency in megacycles, it is taken in the denominator, and delta nu is taken in the numerator. So for this, for methanol, as we discussed, delta, the chemical shift difference is 139 hertz when they are measured in terms of frequency variation. Then when you are substituting in the above relation, 139 hertz divided by 100 megahertz as the applied frequency, then we'll be getting 1.39 ppm. But that 139 hertz is equivalent to 3.26 micro Tesla in terms of the applied field. Then 3.26 micro Tesla, which is divided by 2.3487 Tesla, which is nothing but the applied field, which is equivalent to that of the 100 megahertz frequency. Then it could be obtained again as 1.39 ppm. So in either way you calculate, the chemical shift value doesn't vary. Even if the frequencies are, the applied frequencies are doubled, here also we'll be getting doubling and the chemical shift difference. And here the applied field also is doubled, then also the chemical shift difference gets doubled. Then finally, we'll be getting delta again as 1.39 ppm only. So that is the chemical shift will never change. It will still have 1.39 ppm. So you can vary the frequency or you can vary the applied field strength. But the representation of the shifts, it is done using chemical shift values, which remains same. So the references, these are the books.